Hi, kids. All right. You should have done a lab where you figured out the equation for kinetic energy. Um, so let's just make sure this makes sense. So you started with a cart that was attached to a spring. The spring was stretched out, and then later on, the cart was now moving that way. Okay, and the spring was not stretched out. Okay, um, so a couple of things. Our system, because again, remember we have to identify our system. That if we say our system was the cart plus the spring, that means what is available to our system is kinetic, because an object moving can have kinetic energy, plus US is in our system. Okay, if we said our system was just the cart, then you'd only have kinetic energy. If you said your system was just the spring, then you'd only have spring potential energy. But if you have both, then those are both available to my system. Okay, so you were supposed to do some, well, let's do this. So I'll call this part A and this point B. So there's my picture, and then if you're going from A to B, you start with US and you end with K. Okay. And then because it says we're supposed to assume it's frictionless, so going from here to here, there's no outside force being done. If I was drawing my net force, I would have the spring, but that's part of my system. So there's gravity, but that's not going to do work on my system. There's the normal force, but that's not going to do work on my system. So then all of this US gets converted to this because there's no outside work on my system. That's the whole work energy theorem thing. Okay? All right. And then you were supposed to set it up so you knew you could find this, and then you were going to try to find this, and then you're going to find the speed, and then you were supposed to graph kinetic energy, which remember is measured in joules. Okay? And speed, which is measured in meters per second. And when you graphed it, you should have gotten a graph that looks something like, okay? And you should have found that kinetic energy was proportional to speed squared, which means that you're supposed to linearize it, which means you would have had kinetic energy, which is measured in joules, and speed squared, which is going to be measured in meters squared over seconds squared. And then you should have gotten a line. That's pretty fun. And then you're supposed to look at the slope. Okay? Well, let's look at the slope. Okay? Slope is rise over run. So I have joules over meters squared over seconds squared. Okay, so joules. So what is a joule really? Remember, a joule is just like with work, it's force times distance. Okay? So a joule is really a newton times a meter over meters squared over seconds squared. Well, what is a newton really? Oh yeah, that's a kilogram meter per second squared, m times a, times meters over meters squared seconds squared. Oh look, 1 meter goes away. Oh look, the other meter goes away. Oh look, my second squared goes away. Oh look, I have kilograms. Oh look, that means the slope must be related to the mass. But hopefully you were smart enough to realize that it's not actually the mass. It was actually the slope was equal to 1/2 times the mass. Hopefully you saw that. Okay. So then remember, anytime you got a line, you should be thinking about y equals mx plus b. So in this case, did I graph y? Nope. I graphed kinetic energy. What was my slope? Well, my slope was 1/2 times the mass. And then did I graph x? Nope, I graphed x squared. And so I get my formula, which is this, 1/2 mv squared. And if you look on your handy dandy formula sheet, whoops, it's right there. Okay, 1/2 mv squared. Okay, pretty neat. Yeah, I know, that is pretty neat. So you have that. And then that should have been good for the lab. So, bye, kids.